graph hourly wage at $9 per hour. We see the graph forming straight line with a positive correlation. As you make more hours, you make more money. This is a direct relationship because as one goes up, the others goes up. And of course, if one goes down, the other goes down. Mathematically, we can turn this into algebraic equation. Dollars earned equals to rate called K times the hours of work. Let's say you work 10 hours. 10 times the rate of $9 per hour will give you $90. This pattern and equation work for all direct relationships. So the equation A equals to K times B is the basic equation for the direct relationships. When A and B are the two variables and K is the constant or slope of the line. When graph, we get a line. When you graph the length of the rectangle with an area of 24 cm squared, there's a lot of possibilities. In this case, the length times the width must equals 24 or constant. So we can graph the length of 6 and width at 4 to get our constant 24. But if I raise the length, let's say, to 12 and must lower the width at 2 in order to get a constant of 24. This is an inverse relationship which makes hyperbola when graphed. So the equation A times B equals K is the basic equation for inverse relationship, and again when graphed, it makes hyperbola. We can also find out the kind of relationship is present from collective data. After several trials, manipulating variable A and recording variable B, we can calculate A times B and A divided by B to identify relationships. If the data in column A times B is constant, that shows is an inverse relationship because in our equation A times B equals K, the constant. If however the data in A divided by B column is constant, then this is actually a direct relationship. Remember, this is an algebraic equation, so the equation A equals to K times B can be rearranged to A divided by B equals K, and that's exactly what we have here. Now, the numbers might vary slightly, but those are very clear pattern in the data. If there's a situation where there are more than two variables, you can still figure out the mathematical equation. Here, an example of cat, mice, and days. If 5 cats can catch 3 mice in 5 days, how many days that it takes 3 cats to catch 3 mice? This problem seems very obvious, 3 days, but that's actually not correct. The reason for this comes down to the type of the relationship between cat, mice, and days. So, let's hold one variable constant while we manipulate other two. So, let's look cat's constant 5 and increase the number of mice. If there's a more mice catch but the same number of cats, it's gonna take more time. So, more days to catch them. This is a direct relationship. Now, let's hold mice constant and increase cats. This would take the cats less time to catch the same number of mice. So this is an inverse relationship. Lastly, let's keep days constant and increase the number of cats. And same time, with more cats, they can catch more mice. So this is another direct relationship. Now we can turn this into an equation. Direct relation have the variable on the opposite side of the equation. The constant you could place to the other side. So, mice and days, since they are direct, need to be on the opposite side. Cats and days are inverse, so cats and days should be on the same side of the equation. Cats and mice are direct, so they should be on opposite side of the equation, and they are. This is a final equation. Now, we just calculate the constant k using the number of the first problem. First, we need to get k by itself, so we divide both sides by dc, and we get m divided by dc equals k. Or the number of mice divided by days divided by cats equals to constant k. So back our initial data, which was 5 mice, 5 cats, 5 days, and when you calculate k, you get 0.2. Now, with this information, we can plug in new data, 3 mice, 3 cats with the constant of 0.2, and we can solve for d, the number of days it will take. And it takes 5 days. So even at first we ever thought take 3 days to be caught by 3 cats, it actually take 5 days.